Hello folks, so on this set of videos we'll be going through chapter 16, acids and bases, which means we'll go through the pH scale, we'll reintroduce our friend capital K, the equilibrium constant, we'll use ice tables again, but in a much simplified fashion. We'll learn about the various types of and classifications of acids and bases. So let's go ahead and get started. This first video will just be our introduction into acids and bases. Okay. Yeah. So, the first thing to note is acids and bases were known since ancient times. We're talking about the Greeks and the Romans knew about acids and bases. Since the invention of soap, we've known about acids and bases. But acids come from, I think, Greek acerae, and Greeks, and the bases alkali. We still use alkali nowadays, but acerae, not so much. But when we think of acids typically taste sour. Lemon juice, orange juice, there's a lot of vinegar. All these things are acids and they taste sour in nature. Now bases, when you think of bases, are typically bitter. Now, the main reaction of this chapter is just acid neutralizing base, or base neutralizing acid. Acids can do a lot of different things, but the main thing they do is neutralize bases or react with bases. Now, there are various different definitions of what makes an acid and a base. Each one is more general than the last, but they all, when we change definitions, the purpose is to greater our understanding of what is capable of being an acid or what is capable of being a base. Originally we thought acids had to be, for example, containing oxygen, which is why oxygenos has to do with like sharp causing. Essentially the idea that acids are sharp or sour in nature, and then so a lot of our acids do have oxygens, but things like hydrochloric acid, no oxygen, so that's clearly a bad definition. So our simplest one that we will specifically start with is that of Arrhenius acid and a base. Arrhenius acids generate a proton, a hydrogen positive ion, when dissolving in water. Arrhenius bases generate a hydroxide when dissolving in water. So if it contains a labile proton that can be lost, it's an acid. If it contains a reactive hydroxide, it's a base. Most of our common acids and bases are clearly Arrhenius in nature. However, that is not all the cases. So as I said, many foods are acidic. We have a lot of our fruit, especially citrus fruit. Coffees are mildly acidic. Soda is acidic. Even milk is just mildly acidic. A lot of our medications, including our metal-based ones, milk of magnesia, Pepto-Bismol, bismuth, and magnesium, respectively, are mildly basic. Many of our drugs, both legal and illegal, are bases in nature. Nicotine, caffeine, morphine, cocaine, amphetamines, all of these contain alkaloid backbones that are capable of accepting protons. Now, the stomach is a very acidic intestine. The small intestine, it ranges from mildly acidic, where it you first enter where the acid first comes from the stomach to mildly basic by the end. And our blood is mildly basic. So there's a lot of different situations within the body that have acidic or basic tendencies. A lot of rain is mildly acidic, though certain heavily sedimented lakes and whatnot can be mildly basic, depending on how much sediment, especially calcium sediment, they contain. So, now, the reaction we will see is technically H plus forming, but in reality it's closer to this reaction. And we will use these interchangeably, but we'll try to use this one more often than not. That in water, and the majority of our reactions will be done in water, the proton does not remain just a proton. It will be picked up by nearby water molecules, which are essentially everywhere, and forming a hydronium ion. Hydronium being a H3O plus. Now you can use H plus or H3O plus interchangeably, but it's really more accurate to use H3O plus. So HCl, when it dissolves, breaks apart into H3O plus and Cl minus. Or carbonic acid, when it reacts, will dissociate into H3O plus and bicarbonate ions. Now, this conversion to hydronium is not always complete, and we'll learn more about this later, that an acid's degree of dissociation will directly relate to their K constant. And that K constant will control on whether we consider an acid to be strong or weak. Essentially, with a strong acid, we assume that the K is very, very large, much greater than 1. So that means our products are almost 100%, that we have essentially less than 1% of our reactants left unreacted. There are 7 strong acids, worth knowing. Now, that doesn't mean there's not stronger acids out there, it's just these are the most common ones. Looking at our halogen column, HCl, HBr, and HI. We have left off HF, and we'll talk about HF later. In terms of our oxyacids, nitric acid, perchloric acid, chloric acid, and sulfuric acid. Those are our 7 strong acids that we will see very commonly. As I said, there are more, but a lot of them are organic or very unusual, so we do not see them very often. So remember, the strength relates only to the K value, not to the concentration. It is possible to have a very concentrated weak acid or a very dilute strong acid. And so that will control how much dissociates. Now, Arrhenius base, essentially when they dissolve, they increase the amount of hydroxide in solution. Now, the base can be strong, the base can be weak, depending on that same equilibrium expression of this guy breaking apart. How much does this break apart? Now, our strong bases include sodium hydroxide, lithium, potassium, and rubidium and cesium hydroxide. So all of the group 1 metals version of hydroxides and 3 of the group 2 metals: calcium hydroxide, strontium hydroxide, and barium hydroxide. The reason why the other 2 are not just has to do with solubility. Magnesium and beryllium are not super soluble, and so they are not considered strong bases. Now, these last 3 are dibasic, meaning every time you dissolve 1 molecule of calcium hydroxide, it produces 2 hydroxide molecules. So 1 mole of calcium hydroxide produces 2 moles of hydroxide. And so we have to take that into account when balancing chemical reactions. Now there's a lot of different weak bases that are derivatives of ammonia. Ammonia being the main one, but there's other ones that contain nitrogen groups. And the idea is that ammonia, in the presence of water, will steal one of its protons to form an ammonium and a hydroxide. This splitting of water is called hydrolysis. Hydrolysis, essentially loosening of water. There's a lot of hydrolysis that goes on in the biochemistry, in the field where a lot of chemical reactions involve hydrolysis. Now, ammonia is our first real kind of example of, well, it doesn't have an obvious hydroxide. Yes, in water it does produce a hydroxide, but it is less obvious. So maybe the Arrhenius definition is not the best one out there. So the easiest and better definition would be one that no longer includes hydroxide. So one of the things, we'll move on to a different definition right away, which is called the Bronsted-Lowry acid-base definition. Come out obviously by 2 scientists who got to put their name to it. So in terms of Bronsted-Lowry, we forget about the hydroxide and now understand acid and bases in terms of how they will react with a proton, or hydronium in this case. Under the Bronsted-Lowry definition, acids are things that will donate a proton, while bases are things that will accept a proton. This changes everything in that now we have, in a reversible reaction, an idea of an acid-base pair. That you have an acid and a base in every single side of the equation, and they swap depending on what you have doing. So every acid becomes a base, every base becomes an acid. HF is an acid. It's a weak acid, but it's an acid. It donates an H to form F minus. F minus, if it were to go back, would have to act as a base to accept the proton. Water is acting as a base because it's accepting a proton to become hydronium. But if it wants to go back to water, hydronium needs to act as an acid. So the idea is that we have an acid and a base that forms an acid and a base. Ammonia is a base. It accepts a proton from water. Water's acting as an acid. It forms hydroxide, which is a base, and ammonium, which is an acid. That in order to go back to ammonia, we have to release the NH, release one of my protons. And so ammonia and ammonium are base conjugate acids. HF and F minus are acid conjugate base. And you note water, in this case, acts as both an acid and a base depending on the situation. This is called an amphiprotic molecule. Water is the most common one, but in strong enough acid or strong enough base, many different molecules can be considered amphiprotic. Whether they can accept a proton or donate a proton, depending on whether you're in a strong enough acid or strong enough base. So the one thing is, okay, if everything can be an acid and a base, what makes something an acid and not a base? And that has to do with strengths, our K expression. The K that forces something towards products and not reactants. That the strength of dissociation is going to control whether it goes forward or backwards. A strong acid will always dissociate before a weaker acid. So if I have HCl, which is a strong acid, and I have vinegar, which is a weak acid, the vinegar is going to remain largely unbroken up until all of my HCl has fully reacted. A strong base will fully dissociate before a weaker base. So as long as there's base in solution, the weak base stays together. So conjugate acid-base pairs will share an inverse relationship in their strength. That a very strong acid will form a very weak conjugate base. A moderately strong acid will form a moderately weak conjugate base. And a very weak acid can form a very strong conjugate base. Now this will control the reversibility and the rate of reverse reactions based on the size of these Ks. So the idea here is sulfuric acid. The first dissociation is very strong. It has a K of essentially 1,000. So it's going to go towards products, which makes a very weak conjugate base of the K for the reverse reaction being 1 times 10 to the negative 17th. Now the second reaction, hydrogen sulfate breaking apart into sulfate, has a weaker Ka value, a K of about 10 to the negative second. So this is considerably weaker, but it produces a conjugate base that is a little bit stronger, of 10 to the negative 12th. So it still wants to dissociate as an acid, but it's not necessarily product favored as we would have liked it to be. So now water, as I said, can act as an acid or a base depending on the situation. But what is special about water, and usually most solvents honestly, is that it will do both simultaneously with itself. That this process is called autoionization. That water will cleave itself to form hydronium and hydroxide. The degree of this largely has to do with another K expression. It's not very big, but it does happen. The rate of the reverse reaction is very rapid, so no one water molecule stays ionized for very long. So even though we're drinking pure water, there's trace amounts of acid and base, but not nearly enough for it to actually ever hurt you. But we do have a very small equilibrium constant, and this reaction does occur. And so that's something to keep in mind. With relating to this, we are going to look at the K expression. So remember, K is products over reactants. We will ignore pure solids or pure liquids. So for that last reaction, H2O goes to H3O plus and OH minus. H2O is a pure liquid. So H3O plus and OH minus are the only parts of that K expression. So we're going to call this special expression KW for the autoionization of water. And so the hydronium and hydroxide concentration directly relate to each other on the or indirectly relate to each other by the factor of 1 times 10 to the negative 14th when at 25 degrees Celsius. So this is a very, very small value. But what we can see is that since this is equal to just two things, they're interrelated. That we have hydroxide and we have hydronium, but as one goes up, the other must go down. So when we measure acidity, we have to deal with the ratio of acid to base. There will never be pure acid with no base or pure base with no acid. It's just the base may be so small we cannot easily measure it. So when we talk about an acidic solution, we have a greater quantity of acid floating around. In a basic solution, we have a greater quantity of base floating around. When we have a truly neutral solution, we have equal quantities of both, and we say that the concentration is 1 times 10 to the negative 7th. And this is our solution, our neutral solution. Well, that's where we're going to end this video for today. In the next video, we will look at how we measure acidity, which is the pH. So I'll see you then.